All right, we're continuing on with 15.3 today. There's one little example that we need to go through to finish up 15.3. And then we're going to start on 15.4, which is talking about titrations and pH curves. So let's just go ahead and with 15.3, oops. This will be 15.3 continued because we kind of did most of the stuff from 15.3. But the last thing in 15.3, and we'll just still call this A, would be preparing a buffer And with preparing a buffer, a common type of problem would be that you'd be given a list of a bunch of different acids and you'd be asked, well, which one would be the best one to choose to make a buffer that would give you a certain specific pH. So we'll say which acid, and since we're talking about buffers here, it's not just the acid by itself, it's which acid with their salt as well, because we need both to have a good buffer here. So which one would make a buffer with a pH of 4.30? Okay, so I'm given the pH value, and then you'd be given a list of a bunch of different acids. So maybe chloroacetic, and then their Ka values. So Ka would be equal to 1.35 times 10 to the negative third. Propanoic, and you don't need to necessarily write all of these down, but the process afterwards will be important. 1.3 times 10 to the negative 5. Benzoic acid, Ka equals 6.4 times 10 to the negative 5, and then hypochlorous. And Ka equals 3.5 times 10 to the negative 8. So the question is, which one of these acids with their sodium salts or with any of their salts would make a buffer with a pH of 4.3? Now I know that from Henderson-Hasselbalch equation, pH equals pKa plus the log of my concentration of the base over my concentration of the acid. And you can kind of assume, since we want there to be a good buffer here, we want to pretend like it's going to be an ideal buffer, which means that if I have an ideal buffer, this ratio is equal to 1. And so then if I take the log of 1, it equals 0. So that part of the equation goes away. So in finding an acid that would give me a pH of 4.30, that's going to be equal to the pKa. So I want to find out the pKa's of all three of these guys by just taking the negative log of them. So I'll just say up here, the pKa, if I negative log each one of those Ka values, for the first one I would get 2.87, then 4.89, 4.19, and 7.46. And so what I want to do then is, since I'm trying to figure out which acid would make a buffer with a pH of 4.3, I'm going to pick just whichever one is the closest. And so 4.19 is the closest, so that means benzoic acid along with its salt would make a buffer solution that had a pH closest to 4.30. Okay, simple enough. Just looking at Ka values basically. Okay, let's go ahead and go to 15.4. which is titrations and pH curves. Okay, first of all, the titration process. and we're going to do a lab on this next week. We'll do a little titration lab. Basically, with a titration lab, you've got this thing called the burette. And most of the time in the burette, you have some kind of base, sodium hydroxide or whatever it is. Then you've got your container over here, some flask that has acid inside of it. And we're going to add a little bit of base over time to try and neutralize this acid. And then also we're going to have a pH meter, which will read the pH values after we add certain amounts of bases. So you would, in doing a lab like this, which we'll do next week, you'll have your volume of base added, and then your measured pH. So you'd say, okay, if I add 1 milliliter of sodium hydroxide, what's the pH? 2 milliliters of sodium hydroxide, what's the pH? And so on. And then, let's see, we'll go here. The equivalence point. The equivalence point is a very important concept to understand the definition, and to understand when you've reached the equivalence point. It is when the number of moles of acid equals the number of moles of a base. Okay, that's the equivalence point just by definition. And there's a couple different ways that you can tell. Experimentally and even mathematically, as we go through the problems, you'll see when you reach the equivalence point in your calculations, you have the same number of moles of acid as you do moles of base. Now, we'll say number one, how do you know you've reached it? In doing a titration lab or in looking at titration data, how do you know when the equivalence point has been reached? Well, there's a couple different ways. First way would be a color change of an indicator. The most common one, and we've talked about this already, is phenolphthalein, which is spelled crazy, but phenolphthalein, if we start with an acid, phenolphthalein is clear in an acid. So when I add enough base to completely have the same number of moles of it, and then it'll like barely get a little bit extra base than acid, then I know it'll turn from clear to pink. Phenolphthalein turns pink when it's basic in solution. So when you get that color change, you know, okay, I have the same amount of moles of everything. If you have bromothymol blue, and we've talked about this before also, and this is the situation I'm dealing with here, it's yellow in an acid, so it would be yellow to begin with, and once I've added enough base to reach the equivalence point, it would change to blue. Now the second way, that's the first way, is the color change of an indicator if you have that. But if you go through and you use the pH meter and you record all these different pH values after you add certain volume of base and you graph it, you'll end up with, let's see, we'll make this B. So the first way is color change of an indicator. The second way is to chart it with the pH meter. And then you do a little graph of pH. And then this is like volume of base added. When you do that, you get a graph that looks kind of like this. The center of the steep part of that graph is the equivalence point. And so you can kind of go over and see what the pH value would read at that point. So center of steep part of graph equals equivalence point. Okay, so let's do a simple titration calculation here. So we'll call this strong acid base titration. I'm just going to do an example and then we'll draw the graphs. Okay, let's say that we've got 50 milliliters of 0.20 molar nitric acid. It's titrated with 0.10 molar sodium hydroxide. And I want to calculate the pH after, and then we're going to have several different situations here. Okay, so it's, let's take a look at my graph over here, or my diagram, I should say. In here I've got nitric acid, and I'm going to add some sodium hydroxide, NaOH, to it, and I want to figure out pHs after I've added a certain volume of sodium hydroxide. So if I add 10 milliliters of sodium hydroxide. Okay, first of all, you should kind of think about what you have going on in the beaker, right? I've got sodium hydroxide that I'm adding, so that separates because it's strong. I've got nitric acid, which separates. Sodium, nitrates, don't matter. My reaction when I am titrating strong acids and bases, when I'm mixing strong acids and bases together, is H plus OH minus, and that gives me H2O. All I care about here is the hydrogen and hydroxide ions. What I want to do is I want to figure out how many millimoles I have of everything. Okay, so I've got 50 milliliters of 0.2 molar nitric acid. So that's going to give me, if I multiply 50 milliliters times 0.2, it's going to give me 10 millimoles, and that's going to be my starting number of millimoles of hydrogen. Now with hydroxide, if I'm only adding 10 milliliters of it, and it's 0.1 molar, 10 times 0.1 gives me 1 millimole. Okay, and I'd have 0 of this to begin with. Now hydroxide is going to be limiting here, so this is a BCA table. This is stoichiometry, not equilibrium. I would do -1 gives me 0, -1 gives me 9. I don't care about water at all because it has nothing to do with the pH. And so my hydrogen ion concentration is 9 millimoles over, now my total volume, I'm trying to find molarity here, so I need millimoles over milliliters. I had 50 milliliters of nitric acid to begin with. I added 10 milliliters, so my total volume is 60 milliliters. So that gives me a concentration of 0.15 molar, which then you can just negative log that to give you the pH value to be 0.82 after adding 10 milliliters of sodium hydroxide, 0.1 molar, to my 50 milliliters of nitric acid. Now, your problems in your homework, which is just going to ask you guys to do this for different volumes of sodium hydroxide added. So let's do, let's see, so that would be before we've reached the equivalence point where we still have hydrogen left over. Let's do, if we did another one like that, it would be the same exact thing. Before the equivalence point, you'd have hydrogen left over. Let's do, if I add 100 milliliters of NaOH. And again, I can start right here. Hydrogen plus hydroxide gives me H2O. My hydrogen concentration is the same because I don't add any more nitric acid. I still have my 10 millimoles of hydrogen ions. Sodium hydroxide, I'm going to add 100 of it, 100 milliliters times my 0.1 molar. That also gives me 10 millimoles. Now, I've got the same amount of moles of both here. So this is the equivalence point. Okay, and that means I'm gonna lose 10 of everything. I'm gonna have minus 10, 0 hydrogen, 0 hydroxide. And I'm gonna have 10 millimoles of water. Okay, if I do the stoichiometry for that. So in calculating the pH, this is kind of tricky. For a strong acid and a strong base only is this the situation. All I have here when I'm calculating pH is the concentration of hydrogen ions from the water. And I know because of the autoionization of water, that water has a concentration of hydrogen ions of 1 times 10 to the negative, oh, not 4, 1 times 10 to the negative 7. So then that gives me a pH of 7, which we know to be the neutral pH. So when you have a strong base and a strong acid, one is titrating the other, and you're at the equivalence point, the pH is going to be 7, but only if you have a strong acid and a strong base. When we get into on Wednesday weak acids and stuff like that, it'll be different. But if you have strong of both and they reach the equivalence point, then the pH is going to be 7. Okay, so you're going to go through that process and you'll find pH values for different amounts of base that's added to an acid. Now real quickly, the titration curves. We are going to, let's see, if I have a strong acid and a strong base, or I should say strong acid with a strong base, meaning I've got the strong acid in the flask and I'm adding a base to it, then my titration curve, I'm going to start off with a very low pH down here, and as I add volume of base to it, the pH is going to increase, and then I get this steep line thing. We already talked about this. This is my equivalence point, and that pH for a strong acid and a strong base is 7. If I have a strong base titrated with strong acid, then it's the same idea, it's just that my pH starts out higher because I start with the base in my flask and I add acid to it, and then my pH decreases. Right here is my equivalence point, and again that pH will equal 7. Only the equivalence point pH is only 7 when you've got a strong base and a strong acid titrating one another and you have the same amount of moles of both, then they neutralize one another and the pH is 7. This down here would be the volume of acid added. Okay, you have an assignment to work on that is due on Wednesday, and let's see, it's page 741, 45, 47, 48, 53, and 54. There's some buffer types of questions and then strong acid-base titrations. I'm going to give you guys, oops, you can't see that. There you go. I'm going to give you guys a little quiz on Wednesday just to see that you've gone through and watched the lecture, that you have gone through and attempted the problems. Your quiz on Wednesday will include one buffer problem which is from last week, Friday, and then also 1 strong acid, strong base titration.